Hello friends, my name is Ashmita Dwivedi. I am an assistant professor at Shri Ram College, Jabalpur. In my first lecture, we talked about the unit-2nd of B Pharmacy, 4th semester, that was RHEOLOGY. So we were discussing about RHEOLOGY. I had given you some briefs about the RHEOLOGY, what is RHEOLOGY, what type of fluid a liquid can show, like Newtonian and non-Newtonian. Then I discussed about the Newtonian flow. Let's see some of the like revisions. What RHEOLOGY basically means? Rheo means to flow, logos means science. So the definition would be, it is the branch of science in which one studies about the flow of a liquid or of a fluid is known as rheology. And two types of flow any liquid can exhibit, that is Newtonian fluid, Newtonian flow and non-Newtonian flow. Newtonian flow, we discussed the liquids which obeys the Newton's law is known as Newtonian fluid, and which does not obey the Newton's law of flow, those are known as non-Newtonian fluids. And what is now Newton's law? Newton's law states that the shear stress is directly proportional to the rate of shear strain, that is tau. We saw it yesterday, like tau is directly proportional to dV by dr, and if removing by proportionality constant, it will become eta. Tau is equals to eta dE upon dr. And we saw the shear stress, and then what is rate of shear strain, and then we were talking about the non-Newtonian fluids. Okay, so I will tell you about some corrections we have seen in my last lecture in the non-Newtonian fluid in plastic viscosity. First, we are looking at the Newtonian's flow, right? So what are Newtonian flow? Newton was the first to study flow property of a liquid that obeys Newton's law of flow are Newtonian fluids. So capital F force is equals to eta and G. Force, this is the force per unit area which is applied on a liquid. Eta is represents viscosity and G is shear strain, right? And the graph of the Newtonian flow will be, it is the graph also known as rheogram. We call it as rheogram. So the rheogram will be in between rate of shear strain and shear stress. F is shear stress and G is shear strain. And this rheogram passes through the origin. This is known as origin, right? So rheogram passes through origin, and this slope gives the coefficient of viscosity. This slope is known as coefficient of viscosity. So the system that follows linear, this is also known as linear relationship between shear stress and shear strain. So the liquids which follows Newtonian's flow are like water, we saw yesterday. Glycerine also follows Newtonian's flow. Then chloroform is there, right? So now we will be discussing about the non-Newtonian fluids, non-Newtonian flow. Yesterday we saw about the plastic flow. And what was plastic flow? Like until and unless a shear stress more than yield value will be applied on a particular liquid to flow it will not flow. What I mean by this is, we saw the rheogram, right? Actually yesterday I told you the example about the ketchup. That was not the, here minor correction is required, that was not the like example of plastic flow. That was the example of pseudo plastic flow we are going to see after the plastic flow, right? So what happened basically in plastic flow? I will tell you some examples which shows like plastic flows are suspension, butter, ointment, paste. These are some formulations which shows plastic flow. Means until and unless, this is the graph, you can understand it by a graph. This is the shear stress which is represented by capital F, and this is shear strain on y-axis, that is G, right? So we saw that the graph of a plastic flow does not start from the origin. This is the origin. It does not start from the origin. because initially it does not flow when we apply a shear stress on it, until and unless it will not achieve a yield value. The gap between these lines is the yield value. So until unless it will not get the yield value, it will not start to flow, right? So this was all about the plastic flow. The slope of this plastic flow represents mobility, right? I hope you must have understood it. Increase in the shear stress, non-linear increase in the shear rate. This is not the linear relationship you are observing. This is the non-linear increase in the shear rate, which further progressively linearized. It is getting linearized, but after a yield value, right? So this was all about the plastic flow. Now, what is yield value? Yield value is the stress which is required to break interparticle contact between the materials exhibits plastic flow. This is also known as Bingham bodies. We saw it yesterday. The definition of the yield value will be the stress required to break the interparticle contacts between that fluid, right, is known as yield value and Bingham bodies. And we saw the equation yesterday, that is capital U is equals to capital F minus small f upon G, right? U is the plastic flow, capital F is the shear stress, small f is yield value, and G represents shear rate, right? Here you can say with an example, like this was the suspension or paste which is showing the plastic flow. Here, until unless an yield value will be applied here, the interparticle contacts between these particles will break, and further upon increasing the stress it will start to flow. So this is all about the plastic flow. Now we will see the next one, that is the pseudo plastic flow. Pseudo means what? Pseudo means false plastic, right? So we'll decode it further. Here what actually happens, here also the consistency curve, or you can say the rheogram or the graph between shear stress and shear strain begins at origin. Here you can see the graph. Here the rheogram between rate of shear and shear stress starts from the origin, but it is also non-linearized. Why these graphs are non-linearized? Because these are non-Newtonian fluids, right? So what basically happens in a pseudoplastic flow? Yesterday I told you about the plastic flow, the ketchup example. The ketchup is an right example for pseudoplastic flow. How? What happens? Suppose you have a bottle of ketchup, right? So what happens under normal storage condition? The ketchup molecules are randomly arranged in the dispersion. But when you are applying the shear stress on it, the molecules which are attached to the chain arranges their excess. Here the molecules you can see are randomly arranged in a chain. When you will apply a small amount of stress, polymer they will orient, the molecules of the ketchup will orient themselves in the direction of the applied force. Then further what happens? It starts to flow. Once it is in storage condition in the bottle of the ketchup, it is in thickened state, right? These are randomly arranged. But when you are applying a certain amount of stress, fluidity will come into it and it will start to flow, right? So this was the explanation of the pseudoplastic behavior. This behavior is also known as shear thinning system. Why shear thinning system? Because after applying the shear stress, it will flow from the bottle of the ketchup, right? So the consistency curve flow begins at the origin as shear stress increases, shear rate also increases, but the trend is non-linear, right? And the examples of the fluid which show pseudoplastic flows are polymer dispersion, tragacanth in water, sodium alginate in water, methyl cellulose in water, CMC in water, right? So I will tell you once again the explanation. Look what happens. Under normal storage condition, long chain molecules of polymers are randomly arranged in dispersion. On applying shear stress, molecule begins to arrange their long axis in the direction of the force applied, like I just told you. In the direction of the applied force, the molecules of the polymer arranges themselves in the direction of applied force. The stray induces the orientation, reduces the internal resistance of material. So the internal resistance of the material decreases and it starts to flow basically, right? And this was the graph. This is the rheogram between the rate of shear and shear stress. It starts from the origin, but the trend is non-linear. This graph is of pseudoplastic flow, right? Now we talk about the dilatant flow. Dilatant flow is also known as shear thickening system. Why it is called a shear thickening system? Because once a certain amount of force is applied on it, the fluid becomes thick after a certain time period. The system exhibits enhanced resistance to flow with increasing rate of shear. In the pseudoplastic flow, what were happening? On applying the shear stress, the liquid was getting thinner. But here, when we are increasing the rate of shear, the fluid is thickening. Fluid is getting thick by increasing the rate of shear. When these systems are when sheared increases their volume and hence called as dilatant. Why these are known as dilatant? Because once, if suppose we have a liquid in a container, we have this dilatant flow fluid liquid, right? So once a certain amount of force will be applied onto this liquid, it will become thick. What were happening in the pseudoplastic? When applying a certain amount of force, it was getting thicker, right? The resistance were getting reduced. And in this system, dilatant fluid, when we are applying certain amount of pressure, it is getting thicker. Here the resistance is increasing in the dilatant because when it is getting sheared, the volume of this liquid is increasing. That's why these are known as dilatant, right? So these are also known as shear thickening system because of increased apparent viscosity at higher rate of shear. What is happening here? As the shear rate is increasing in this fluid, the apparent viscosity is getting increasing of this fluid, right? I hope you must have understood the concept and the difference between the pseudoplastic and dilatant flow, right? What happens once when shear is removed, system returns to its initial state of fluidity. Okay, so what happens here? Once it is sheared, it will become thickened, and when the stress will be removed out from this container, then it will return to its initial state of fluidity, right? Now the fluids which shows dilatant flows are suspension containing increased concentrations of solid more than 50%. If there is a suspension in which solid content should be more than 50%, then it will show dilatant flow, right? And suspension of starch in water. This is the very big example of dilatant flow someone can imagine. So there is a starch in water, right? If you will increase the force on it, if you will constantly hammer the solution of starch in water, it will become thickened, right? And once when you will remove that hammer from this particular liquid, it will return to its fluidity, right? So this is basically the concept. And the inorganic pigments in water, kaolin 12% in water, zinc oxide 30% in water. These are the some examples of dilatant flow. I hope you must have got some clarity about the plastic, pseudoplastic and dilatant flow behavior of a liquid. I think this is enough for this lecture. And if you have not understood anything up to now, like the non-Newtonian flow, I am free to discuss anything. I am free to resolve any issues if you are having with these flow behavior. If you are liking, I am trying my best actually, and even I can make you understand in a better way. If you want me to explain in a more better way, I am very free to receive the updates from you. If you are liking my video, please like, share and subscribe. I would love to. And okay, so this is now for today, and we'll be seeing like more explanation about it, and we'll discuss more things on this from this unit. Okay, thank you so much.